In this video, we're going to go back and look at what happens in between the initial and final states of a charging or discharging capacitor. Specifically to look at how there is a predictable relationship between the current, voltage, and charge in the circuit as a function of time. So the big question would be, what determines how things charge up? Well, there are a couple of different things that we can think about. There's the voltage of the battery, certainly that could be an effect. There's the capacitance of the capacitor, and then there's maybe the resistance of the light bulb. This is a demo that we didn't really do in detail this year, but if you were to put a long bulb and a round bulb in the same circuit and hook it up to the same capacitor and the same voltage, you would find out that the bigger the resistance, the longer it takes to charge, which hopefully makes sense, because the larger the resistance, the slower the current flows. And the slower the current flows, right, that means less charge per unit time. And we have a certain amount of charge that this capacitor can hold with a given voltage. So if you keep the voltage the same, the only thing you do is change the resistance. You just slow down the rate at which the capacitor fills up. It still fills up to the same amount. So what is it that matters? Well, it also turns out that the bigger the capacitor is, the longer it takes to fill up. And again, hopefully this makes sense, right? It's basically a bigger bucket, and you're pouring water into it at the same rate because you have the same resistance and voltage in your circuit, and it's going to take longer to fill up. So here's a quick little video of a capacitor and light bulb, right? We see that the light bulb goes out, right? And if you can see on the oscilloscope behind the experimenter, right, we see that there's some amount of current kind of changing over time. So that means that we need to think of this in terms of a time constant, a decay function. And so if you think about nuclear decay, that's a good model here. We know that as resistance increases, the time it takes to charge up a capacitor will increase. We know that as capacitance increase, basically making the bucket bigger, it takes longer to fill. So we end up with a time constant. This is a tau, Greek letter tau, is resistance times capacitance. You might say, how does that make any sense? How is that time constant? Well, it turns out that if you look at all the units, it works out just fine, because a farad is, got all those units of charge in it and everything else. And resistance has both current and voltage as ways of thinking about it. Here are the units: a volt per amp, a coulomb per volt. The volts cancel out, but what is a coulomb and an amp? So we get seconds. Yay! As it turns out, right, if you were to charge up a capacitor, we might ask ourselves, which of these graphs is the most logical shape? B would be indicate that it goes at a constant rate. C would be it starts out slow and speeds up, and A would be it starts out fast and slows down. And the way to think about this is it easier or harder to put charge onto the capacitor at the beginning or end, or does it not change at all? As it turns out, A is the best answer, and that is because as you add charge to the capacitor, initially it's empty. And unlike a bucket, where filling it with water at a constant rate would mean it would fill up at a constant rate, as you fill up the capacitor, you now have positive charge on the positive plate, negative charge on the negative plate. And if you want to put another negative on the negative plate, it's now harder to do it because there's negative charge there repelling you, right? As it charges up, it gets harder and harder to add charge to that plate, right? You've got some positive and negative now on that plate. On those plates, if you try to add more, it's more difficult. And eventually, the final value of the charge that's on that plate is equal to the capacitance times the voltage, Q equals CV. That's what we learned back when we started talking about capacitors. So we've got this general shape, steep at the beginning, flat at the end, approaching a value of Q equals CV, or Q equals C epsilon, where that's the EMF of the battery. This is basically a differential equation. Similar simulations or situations that we've already looked at are drag. We haven't actually gotten into all the details of that. We'll come back to it. But LR circuits and magnetic dampening also behave this way, which we'll learn about in Unit 11 as we wrap up the year. So what does this look like? We know that at the beginning, V equals, for the entire circuit, V minus, of the battery, minus IR, which would be the voltage across the resistor, minus Q over C, which would be the voltage across the capacitor, should add up to 0. And if we let current be dQ dt, we have a nice differential equation. Very exciting. And we've got our time constant, RC, there. If we actually solve this, separate and integrate, we end up with this lovely results. Raise it to the power of E, to get rid of the natural log. You might be saying, Mr. Grams, I'm not following this. That's okay. You end up with this result. Now, you are not responsible for solving that differential equation. You are simply responsible for looking at this equation with the time constant, where Q is equal to CV times 1 minus E to the negative T over tau, with some related ideas. But this is the amount of charge you have over time. And so basically, when T gets really big, infinitely big, this is e to the negative infinity, which means it's just 1 times the maximum charge on the circuit. Or, as we usually write it, Q final times 1 minus e to the negative T over tau. So both of those are kind of ways we think about this. This is the graph. This is the shape. It's a decay function approaching the final value of charge on the circuit. So at time 0, it's e to the 0, right? So that's 1. So we get 1 minus 1, 0. At time infinity, we get Q final. Those are the extremes. And so this is the stuff at the initial and the final is what we already looked at the initial and final states of a capacitor circuit. At T equals 1 tau, we're at 63% of its maximum charge. And that's kind of how the time constant behaves. And again, if you think about nuclear decay and that kind of thing, stuff you've looked at probably before in math and maybe chemistry, that should be familiar. This is kind of a picture of how it goes, right? After 1 time constant, you're at 63%. After 2, 86-ish%. After 3, at 95. And so oftentimes you would say it's sort of 3 time constants is a reasonable amount, 95% of the way there, or 5 time constants, you're into the 99%. And so this is a good rule of thumb if you're thinking about how long should I let this charge before I say it's fully charged. 5 time constants is definitely getting you to a place where probably it's fully charged to the ability of your measurement devices to measure. So I have done a data collection here of charging and discharging an RC circuit. I showed you a similar graph of this when we were looking at how capacitors behave in that first video on capacitors. But basically, you've got the current, right, which is decaying over time, and you've got the voltage, which is growing or decaying over time, depending on whether it's charging or discharging, right? So we might want to think about this stuff in terms of not just the charge on a capacitor, which is a thing that's hard to measure, but current and voltage, which are easy to measure. It turns out that you can find the total charge by taking the area under the curve of this current versus time. And then if you're looking at the shape of the curve for this voltage graph, well, we know that the charge follows this same shape and that the charge has to do with the voltage and the capacitance of the circuit. So you can actually work backwards and figure out how much charge is on there from either one of these methods. You can also see it discharging. Discharging, the current's flowing the opposite direction. Discharging, you start at a positive voltage and you decay down to 0. Same basic shape. And the nice thing is that for all of these, for the charge, the current, and the voltage, we're dealing with the same time constant, RC, right? You've got the same shape, the same time to decay. And, you can work on all those things. You've got the initial, the maximum current, the maximum voltage, and that kind of thing. So this is something that you can fill out in your packet as well. But at time 0, the switch is set to close. What is the shape and the maximum values of all of these graphs? Well, we know that the charge grows until it gets to a certain value. We know that the current starts out high and decays down. We know that the voltage of the capacitor, by definition, should, let me go back. And the current is just Ohm's law, voltage divided by resistance, max current. The capacitor voltage should grow, and we know if we just rearrange that equation Q equals CV, if we arrange it for V equals Q divided by C, right, that should be the maximum voltage of the battery, the EMF. And then finally, for the resistor, well, the resistor starts out, it has to follow Ohm's law, so it has to follow the current. When it has maximum current, it has maximum voltage, starts out with the total voltage of the circuit, and it drops down to zero over time. So let's look at the equation we would deal with for current, right? To find the current over time, you just take the derivative. dq dt is there, right? That's what we do. We can integrate this. Q, we integrated the whole equation before, separated and integrated, but now we get Q as a function of time. And if we take the time derivative of that, we end up with current is the initial current times e to the negative t over tau. And this, of course, will decay down from some maximum value. When t is 0, you'll get total current. And when it's infinitely big, you have e to the negative infinity, and so this will be 0. That's why it looks like that. At time equals 0, the current is equal to the total current in the circuit. At time equals infinity, it is 0. And at 1 tau, it's at 37% because it's changed by a factor of 63%. And that's what it looks like. So page 53, you can kind of do these for all of them: the current, the voltage, and the of the capacitor, and the voltage of the resistor by filling them in. Right, the time constant is RC. The current decays. The voltage for the capacitor grows. And so how do we get that one? Well, voltage is just going to be Q over C. We already have a formula for Q as a function of time, divided by the capacitance, and Q equals capacitance times voltage of the circuit, and we get this where it grows to meet that final value. So we've got that one. And the final one is going to be the resistor's voltage. Well, the resistor's voltage should start high and decay down. So since we know that this is current times resistance, we already have the current formula. It ends up being V naught times e to the negative t over tau. We can also do the same for discharging. It's very similar. The current is just in the opposite direction. The voltage of the capacitor starts high and goes low. The voltage of the resistor will start high and go low, but in the opposite direction, negative voltage. We've got our values. Let me move my little tools out of the way so you can see it. You've got voltage of the capacitor and voltage of the resistor. So let's look at another circuit here. Here we've got 3 capacitors in parallel, right? All the same. And we've got 2 resistors in series. So in order to talk about the time constant of this circuit, we need to understand what is the total capacitance, right? The total capacitance is 0.3 microfarads because you're adding them up. And we've got a total of 20 ohms of resistance, and so we get 6 seconds for our time constant. How long will it take the capacitor to reach 1.6 volts? Well, for that, we can plug in 1.6 volts and solve for the time constant. That you'll need to do a little bit of work, and you end up with 4.6 seconds. You can also think about the fact that 63% is your one-time constant. If you want to think about that, your time constant is 6 seconds, so this has to be less than that. So yeah, when we're looking at these kind of graphs, it's important to be able to find the time constant, either from the circuit itself or by looking at the shape of this, right? We have time. The easiest way to do this is to find it from the equation. So if you have an equation that's in that form, e to the negative t over something, you know that that something is your time constant. But also you can look at the graph and you can say, well, at 100 seconds, I have a particular voltage. You can plug in those values and solve for the missing time constant. The units have to be seconds because e to the negative, something with seconds over something else, would not give you a proper function that you could solve. That's it. We will talk a little bit more about capacitors and the physical properties that make them up in our next video.